Ladies and gentlemen, dear guests, we are very excited to welcome you to the 13th International Symposium on Pharmaceutical Sciences. Although 13th, it will be the first time virtual. After a long journey of preparations, the day has finally come. Starting from today, in the next 4 days, a fulfilling program will take place. Our program will start with the opening speeches, and we hope that it will be a fruitful event and it will allow the knowledge of our field resonate and reach you through your internet connection this time. Now I would like to invite the chair of the symposium and the Dean of Ankara University Faculty of Pharmacy, Professor Dr. Asuman Bozkır, to make her opening speech.
Dear President and Vice President of Ankara University, dear Deans, dear participants and distinguished guests, as the Dean of Ankara University Faculty of Pharmacy, it is my great pleasure to welcome you to the 13th International Symposium on Pharmaceutical Sciences. On behalf of the organizing committee, I would like to express my sincere appreciation for your valuable contributions. As we all know, the COVID-19 pandemic is still ongoing, and its vaccination programs are proceeding throughout the world. However, during 2021, we continue to face travel bans, governmental and contract restrictions in many countries. Therefore, this symposium has been organized as a virtual event for the first time in its history due to the COVID-19 pandemic. This symposium provides a valuable opportunity for scientists to gather and share novel developments, ideas, expertise in research, and networking between countries. Ankara University Faculty of Pharmacy is the first faculty of pharmacy in Turkey and was established in 1960. Since the establishment, the institution rapidly progressed and now has very advanced scientific and physical infrastructure. Pharmaceutical science refers to a category of scientific fields and has followed important development processes, mainly in line with the developments in biotechnology, nanotechnology, and health technologies, which are among the priority of the technology fields of today. While realizing the modern requirements, our faculty has a 5-year undergraduate education program since 2005. And besides Turkish, it provides an English language of instruction program since 2015. Dear participants, I would like to thank all the participants and invited lecturers for their contributions once again. As the chair of the symposium, I would like to thank the organizing and social committees for their dedicated efforts. I can say with pleasure that they did a great job so far. On behalf of my faculty members, I would like to thank the President and Vice President of Ankara University for their support. We have prepared a rich scientific program for you consisting of plenary, oral, and poster presentations. Besides, a workshop and a panel with distinguished speakers will be held. This panel will be a great opportunity in terms of bringing together the representatives of the pharmaceutical industry, the authority, and the academicians to discuss the existing practices and the requirements of our country, and also to propose solutions about this important topic. I would like to say with pleasure there is a great interest to this panel from pharmaceutical industry. I strongly recommend with you to visit our website for the details of the program. I am grateful to the Ministry of Culture for letting us to use the museum links and videos during the coffee breaks of the symposium. I highly recommend you watching these short videos about Turkey and also visit virtual museums where you can see views from all over Turkey. Dear distinguished guests, I would like to conclude my speech by expressing my hope that the 13th International Symposium on Pharmaceutical Sciences will be a very successful event with having productive discussions. I sincerely hope you will enjoy today and the next 3 days of our symposium. Thank you for your participation and your contribution.
Thank you very much, Professor Bosker. Now I would like to invite our symposium secretary, Associate Professor Dr. Zerrin Sezgin Bayındır, to the screen to make her opening speech.
And honored guests. As the symposium secretary today, it's my great pleasure to welcome you to the 13th International Symposium on Pharmaceutical Sciences. We have initiated the organization of ISOPS at 2019. Unfortunately, since 2020, we are grappling with the COVID-19 pandemic. Under these quite unusual circumstances, we have worked hard to put together this first virtual symposium in the history of our faculty. I can say that it has been a journey of unknowns for us at times. I'm so excited that we have finally come to the date where we are going to have this wonderful symposium. This year, scientists from 24 countries have so far been registered to ISOPS-13. Our program consists of 40 plenary, 212 oral, and 200 poster presentations. Excellent research works will be presented in different sessions. Speakers in the program are uniquely placed in accordance to their area of expertise. I would like to refer also to other initiatives that will take place in our symposium. A workshop on employability of the graduates of the Faculty of Pharmacy in Europe will be held with the contributions of the distinguished professors and young pharmacists. Especially this workshop will be interesting in terms of discussing the priorities and developments on this topic from local, regional and international respects. On the 25th of June, you are invited to attend our panel on university, industry, public sector cooperation in drug and vaccine development processes. We have scheduled dynamic online poster sessions which will give attendees the opportunity to explore ideas with each other. Please check the poster session link on our website and join the poster session discussions via provided Zoom links. We are delighted to have you join us here today. I hope that you will take the time to listen and interact with the scientific professionals from different disciplines of pharmaceutical sciences that we have brought together for ISOPS. I would like to address my special thanks to our invited speakers and panelists. Saplings will be donated on their behalf as a commemoration of their contributions. As closing, I extend a special thanks to all of my guests, speakers, chairs, and other contributors. I would also like to acknowledge the members of organizing, scientific and social committees who have worked so hard for this meeting. I wish you a productive symposium and hope to host you all in Ankara once again in 2024, face-to-face this time. Thank you very much for listening.
Thank you, Professor Bayındır. I would like to pass the microphone to the Vice President of Ankara University, Professor Dr. Hasan Serdar Öztürk, to make his speech.
Distinguished speakers, colleagues, Ladies and gentlemen, welcome to the Ankara University and the 13th International Symposium on Pharmaceutical Sciences. To our eminent speakers, the colleagues, and all participants who have participated virtually from all over the world, I am greatly honored and pleased to welcome you on behalf of Ankara University, which is celebrating its 75th anniversary this year. We are very much proud of the past of our university. We have been experiencing an unprecedented situation with the global COVID-19 pandemic. ISOPS have been initiated in 1989, and this year, for the first time, it will be held as a virtual symposium. I would like to present my compliments to all academic colleagues and administrative authorities participating in this opening ceremony and express my deep satisfaction for sharing this important moment for the development of pharmaceutical sciences. Our organization committee and also the scientific committee have done a fantastic work for the preparation of this Congress, and I would like to thank them for their energy, effort, competence, and professionalism during the organization process. For sure, the success that I anticipate about this Congress will certainly be the result of the effective collaboration between the faculty and our university. I would like to present special thanks to our chair and dean, Asuman Bozkır, and symposium secretary, Zerrin Sezgin Bayındır, not only for their fundamental work in motivating colleagues for the organization of this Congress, but also for their leadership during the organization and also the continuous communication and coordination. I hope this Congress will provide you all a forum to exchange scientific ideas, inspire new research, and new contacts for closer cooperation so that we can together envisage the future of a promising development of pharmacy on all over the world. I am very proud to declare the official opening of ISOPS-13 Symposium from Ankara University, Faculty of Pharmacy, and I would like to thank you very much for your attention.
Thank you, Professor Öztürk. Thank you, dear professors, once again for the opening remarks. Our wish was to host you in our faculty in Ankara, interact with you, and share the joy in person. As it is not possible, we will pass the vibe through our introductory video. The Ankara University Faculty of Pharmacy was founded on the 16th December 1960, and the education was introduced in the academic year of 1961-1962. It was the second institution introducing a pharmacy program in Turkey. However, Ankara University Faculty of Pharmacy was the first faculty of pharmacy founded in Turkey. The faculty was managed by a core team with limited resources in the early years. In 1970, 10 years after its founding, Ankara University Faculty of Pharmacy has made remarkable developments in every area of pharmaceutical sciences. Today, Ankara University Faculty of Pharmacy consists of 23,000 square meters of closed area. Our faculty has 3 lecture halls with 160 seats each, and 12 classrooms with various sizes. To qualify as a pharmacist, education takes a minimum of 5 years. The students must be successful in lab courses of analytical chemistry, biochemistry, pharmaceutical microbiology, pharmacognosy, pharmaceutical botany, pharmaceutical chemistry, pharmaceutical technology, and pharmaceutical toxicology. Additionally, our faculty has 2 conference halls and 1 meeting room with 400, 260 seats respectively. All meeting rooms are in the service of our students. In the Professional Skills and Communication Lab, the students acquire professional skills with simulation technique and learn practices in pharmaceutical care. There is also an herbarium in which plant samples are preserved. There are also various sports facilities within the campus at disposal of the pharmacy students. The main library of our faculty offers a collection of nearly 15,500 pieces of books, dissertations, and periodicals. Ankara University Faculty of Pharmacy has 3 central laboratories, which are only used for research projects. These laboratories provide all necessary technology for research in pharmaceutical sciences. There is also a research animal unit consisting of various species, which is available for our staff, and it allows them to run animal experiments and phase studies. Recently established Pharmacy Museum, Devices and Chemicals Museum are located in the main building of the faculty. These museums contain a large collection of documents in their archives and cast light to the history of pharmacy in Turkey. There are also a cafeteria and a food court at the service of our staff and students. The Alumni Association was established by the graduates of Ankara University Faculty of Pharmacy in 1991 in order to maintain the connection between the faculty and the graduates. Fitness center and fine arts centers, including music and paintings, are located in the main building as well. 8 student communities operate actively within the faculty and cooperating with their international counterparts such as International Pharmaceutical Students Federation. Ankara University Faculty of Pharmacy is looking forward to the future with confidence with its existing research potential. What is an opening ceremony without music? No, we won't let that happen. Now I would like to invite Associate Professor Dr. Demet Gürhan from Ankara University State Conservatory, Department of Performing Arts, and Associate Professor Dr. Güler Demirova Güyov from the State Conservatory Music Department to kindly perform for ISOPS-13.
Ankara, Ankara, güzel Ankara, seni görmek ister her bahtı kara. Senden yardım umar her düşen dara, yetersin onlara güzel Ankara. Ankara, Ankara, güzel Ankara, seni görmek ister her bahtı kara. Senden yardım umar her düşen dara, yetersin onlara güzel Ankara. Burcuna göz diken dik başlar insin, Ankara. Burcuna göz diken dik başlar insin, Türk gücü orada her zoru yensin. Yoktan var edilmiş ilk şehir sensin, var olsun toprağın taşın Ankara. Üsküdar'a gelirken aldı bir yağmur. Üsküdar'a gelirken aldı bir yağmur. Katibimiz eteği uzun, eteği çamur. Katibimiz eteği uzun, eteği çamur. Katibimi ararken yanında buldum. Katibimi ararken yanında buldum. Katip benim, ben katibim, eline karışım. Katibimin koluna da gömlek, ne güzel yakışır. Lies a day and meine Lieder, durch die Nacht zu dir. In der Stille meiner Lieder kommst du mir. Flüster stark im Rauschen, in des Mondes Licht, in des Mondes Licht, des Beretes freundlich lauschen, höchster Holde Licht, höchster Holde Licht. Lässt die Nachtigallen schlagen, ach, sie flehen dich. Bitte die süßen Klagen flehen sie für mich. Sie verstehen
Thank you very much, Professor Gürhan and Professor Demirova, for the beautiful performance. Dear guests, the opening ceremony ends here. Thank you for joining us. The first session of the symposium is about to start. I'd like to pass the screen to the chair of the coming session, Professor Dr. Osman Bozkır. Thank you.
Good morning and welcome everybody. While opening the first session of International Symposium on Pharmaceutical Sciences 13, I would like to remind the audiences that please feel free to send your questions throughout the live chat box and share your name and surname. We will be asking your questions to the invited speakers during today's session. Thanks to being an online event, today we have 3 invited speakers and International Symposium on Pharmaceutical Sciences 13. Welcome, colleagues, and we are looking forward to hearing your talk today. Now, I would like to introduce our first speaker, my colleague, Sibel Süzen. Sibel Süzen is professor at the Faculty of Pharmacy of Ankara University. Her research is focused on the synthesis and development of antioxidant-based anti-cancer compounds, their biological evaluation and melatonin-based compounds. In drug research, she graduated from Ankara University Faculty of Pharmacy in 1985. After completing her master's degree in pharmaceutical chemistry at the same university in 1989, she received her doctorate in 1997 from the University of Swansea, United Kingdom, Department of Chemistry. She continued her research at Swansea University in various years. She has been a member of European Pharmacopea Expert Group since 2011. In the last 10 years, she has been working as institutional Erasmus coordinator, internationalization and foreign relations coordinator of Ankara University. She has been coordinating to establishing of English taught programs as well as international projects, internship agreements and educational programs of the European Union. I would like to give the floor to Sibel Süzen, who will talk about dual benefits of melatonin analogs as aromatase inhibitors and oxidative stress modulators in breast cancer. Sibel, floor is yours.
Good morning, dear colleagues and participants. I am very happy to be with you today. I would like to thank to Professor Bozkır and the organizing committee for inviting me. It's always a great pleasure to participate well-known symposium ISOPS, which is organizing by my faculty traditionally. Today, I will talk about breast cancer and aromatase enzyme relationship, aromatase inhibitors, and molecules containing indole rings, such as melatonin and derivatives as inhibitors. As we all know, cancer is the second leading cause of death globally. In 2018 data, lung is the most common types of cancer in men, while breast is the most among women. Recently, any statistics released by the International Agency for Research on Cancer in December 2020 is saying that the breast cancer is now overtaken lung cancer as the world's most commonly diagnosed cancer. When we look at the World Health Organization 2020 Turkey fact sheet, in the graph on the left, lung cancer ranks first with 17% for both sexes in the general Turkish population. In the graph on the right, we see that the breast cancer ranks first among women in Turkey with 24%. If you look at the breast cancer types, it is divided into three main subtypes based on the presence or absence of molecular markers for estrogen or progesterone receptors and human epidermal growth factor 2. We can also say there is an unclear subtype as well. Luminal A is the most common breast cancer subtype. This subtype has the highest prognosis among the other subtypes. And most patients with luminal B are elderly patients. They are similar to luminal A in that they are also sensitive to endocrine therapy. HER2 positive breast cancer patients account for about 20%, and the prognosis is poor. In the third subtype is triple negative tumors. We see that 3 receptors are negative, and targeted therapy cannot be used during the treatment, and its prognosis is poor. Many studies have demonstrated a causal association between prolonged exposure to elevated levels of endogenous estrogen with breast cancer, and estrogen is suggested to induce carcinogenesis via estrogen receptor dependent and independent pathways. Aromatase is the key enzyme in estrogen biosynthesis. It is involved in the final stage of biosynthesis of estrogen in the conversion of androgens to estrogen. The enzyme is expressed in various tissues, and it is encoded by a single gene, CYP19A1. Under the condition of breast cancer, aromatase expression is unchanged, leading to local overproduction of estrogen that promotes breast cancer. Therefore, aromatase is considered as a potential target for endocrine treatment of breast cancer, but due to the non-specific reduction of aromatase activity in other tissues, these inhibitors are associated with undesirable side effects such as bone loss and abnormal lipid metabolism. Although several synthetic chemical compounds and nuclear receptor ligands are known to inhibit the activity of the tumor-specific aromatase promoters, further development of more specific and effective drugs without adverse effects is still needed. Numerous classes of aromatase inhibitors were developed, but mainly they are categorized in 2 major classes. These are steroidal and non-steroidal inhibitors. Steroidal aromatase inhibitors inhibit the enzyme irreversibly, which are analogs or derivatives of the preferred androgenic substrates. They can be further classified into competitive inhibitors and mechanisms-based inhibitors. Non-steroidal inhibitors, on the other hand, bind entirely non-covalently and contain a heteroatom, usually nitrogen, that coordinates with the iron atom of Hem group, which block the active site and inhibit the enzyme reversibly. Aromatase inhibitors are also divided into categories based on the order in which they were discovered or synthesized, like first, second, and third generation inhibitors, which comprise of both steroidal and non-steroidal types. If you look at the three groups of molecules, we see the development of aromatase inhibitors. Aminoglutamide is the first generation inhibitor we can see in red in the slide. It was withdrawn from the market because of its high toxicity and lack of selectivity, since it can inhibit other CYP450 enzymes involved in cortisol and aldosterone biosynthesis. The second generation compounds are shown in purple. Fedrazole, which contains an imidazole group, is more selective and potent than aminoglutamide. However, it still exhibits effects on aldosterone, progesterone, and corticosterone biosynthesis. The other second generation compound, formestane, a steroid analog, was the first selective inhibitor used in clinical trial. It was proven to be effective and well tolerated. However, it has poor oral bioavailability. The third generation of inhibitors, which are shown in green, includes two triazole derivatives, anastrozole and letrozole, and one steroid analog, exemestane. All three have shown to be superior to tamoxifen in efficacy and lower toxicity. For this reason, today, the third generation of inhibitors has been recommended first-line drugs for therapy of breast cancer. However, with the broad application of aromatase inhibitors in clinical practices, some unexpected problems are gradually shown up, such as non-responsive responses to some of patients, resistance to inhibitor treatment, and inhibition of some CYP450 enzymes. Therefore, there are urgent needs to discover and develop new generation of inhibitors to overcome the defects. Among the non-steroidal inhibitors, the most studied compounds are indole derivatives, such as melatonin. Melatonin inhibits aromatase activity and also downregulates aromatase expression at the transcription level. Melatonin was discovered and isolated from bovine pineal in 1958. It is the main hormone secreted by the pineal gland, and melatonin is widely known to reduce the growth and development of estrogen-responsive breast cancers. Although its major role is the regulation of the circadian rhythm, melatonin has been studied for the treatment of many cancer and immune disorders. Because melatonin declines throughout life, these declines contributes to many diseases. If we look at the dual effect of beneficial effects of melatonin, the direct free radical scavenging activity of melatonin has been known for about 25 years. Melatonin's antioxidant role lies in its non-receptor interactions with free radicals, as well as stimulating the activity of glutathione peroxidase. There are numerous publications involving the antioxidant activity of melatonin. On the other hand, oncostatic effects of melatonin have been reported in several tumors, such as breast cancer, ovarian and endometrial carcinoma, prostate cancer, intestinal tumors. These oncostatic effects have been attributed to the antioxidative role of melatonin, given that the oxidative stress is involved in the initiation, promotion, and progression of cancerogenesis. Melatonin exerts its oncostatic properties in hormone-dependent breast cancer by interfering at different levels with estrogen signaling pathways, and is able to selectively neutralize the estrogenic effect of the breasts. Although melatonin has a role in the regulation of many physiological processes, therapeutic use is limited because of two major problems. The first is very short biological half-life of melatonin owing to its fast metabolism. Second is the non-selectivity at target sites. Our research group has been working on melatonin analog compounds for about 10 years, maybe more than 10 years. We have synthesized many new indole-based compounds with the modifications we have made on the melatonin molecule. In this figure, we see the main positions where the changes were made on melatonin molecule. In this figure, we see some of the modifications made at the determined positions on the indole ring as an example. One of our important findings is that many synthesized indole derivatives have antioxidant potential, strong antioxidant potential. This activity was studied using many different in vitro assays. Cytotoxic activity of the indole derivatives was also evaluated by various in vitro assays. Today, we have series of indole-based melatonin analog compounds. The series showing the highest activities are listed in this slide. At the beginning of our studies, we focused on the antioxidant activities of the derivatives. Since the antioxidant activity don't occur through the receptor, we used many different tests and methods to identify the antioxidant mechanisms, including electrochemical experiments. At this stage, we couldn't benefit from the molecular modeling studies. Along with the determination of the anti-cancer activities of indole-based analogs, our studies were conducted in partnership with both synthesis, in vitro biological activity determination, and molecular modeling. Here we see the general formula of the most promising groups of compounds that we have working on recently. The first molecule that is shown in red in the first line is an indole derivative with the hydrazone formed from the 7th position. These molecules showed significant anti-cancer potential due to their antioxidant and CYP1 inhibitory activities. Since human CYP1 enzyme can catalyze the metabolic activation of procarcinogens to ultimate carcinogens, the inhibition of these enzymes has been considered as an effective approach to chemoprevention. The second general formula in blue shows indole 2 fluorophenyl derivatives. Their antioxidant activity and protection of neuronal PC12 cells against amyloid beta-induced damage was found promising. Compounds having especially orthohalogenated aromatic moiety exhibited effective antioxidant properties without having any membrane damaging effects. And the last molecule in green represents 2-methyl indole derivatives. And this study is the one I would like to give you more information about. In this study, aromatase inhibition potential of new compounds are investigated and compared with melatonin by 2 in vitro models. First one is direct measurement via cell-free assay, and the second one is the indirect measurements via cell-based assay, where cell proliferation was determined in ER-positive human breast cancer cells in the absence of estrogen and the presence of testosterone. Also, docking studies of active compounds into the aromatase active site was employed to detect interaction with enzyme. We see the substituents of the synthesized molecules in this table. While selecting the substitutes groups, special care was taken to select the most active derivatives of the serial compounds obtained in the previous studies that we carried out in the last 10 years. Okay, first experiment on these compounds was the direct measurement of aromatase activity. This was evaluated by a cell-free in vitro assay using fluorescent substrate and human CYP19 aromatase. Almost all 2-methyl-indole hydrogen derivatives showed moderate to high inhibitory activity at 100 micromolar concentration. In this figure, bars represents percentage values compared to control group for different experiments. Results show that the 5 of the 19 compounds are more active. These are 1C, G, I, J, and Y. So here we see the molecular formula of the 5 most active compounds as a result of direct aromatase activity measurements. These are derivatives carrying fluorine and chlorine in the aromatic ring in the side chain of indole ring. Only the last compound is the hydrogen derivative of nicotinic acid attached to the indole ring. Later, these fine compounds that have high inhibitory effects were tested at 8 different concentrations, and enzyme inhibition curves were obtained. As indicated in figure, all 5 compounds show reproducible and statistically significant inhibitory activity on aromatase enzyme. These 5 compounds, which showed significant and reproducible aromatase and inhibitory effect in the direct measurement assay, were also tested at their various concentrations to evaluate their aromatase inhibitory effect in indirect measurement assay. So, the MCF7BUS cells, which are estrogen receptor positive human breast cancer cells, which depends on estrogen for proliferation, was used. Therefore, cell proliferation depends on biotransformation of testosterone to estrogen via aromatase activity in estrogen-free media. Aromatase inhibitory effect of the compounds was evaluated by detecting cell proliferation on MCF7BUS cells in the presence of testosterone and the compounds within the estrogen-free media. In this measurement, compound 1I and 1J statistically significantly inhibited aromatase activity, and the most active compound was found as 1G. We see the molecular formula of the 2 most active compounds as a result of indirect aromatase activity measurements. These are derivatives carrying chlorine in the aromatic ring in meta and para positions in the side chain of indole ring. So compound 1J is the most active derivative in 2 inhibition tests, and we investigated the interaction of these molecules with the enzyme using molecular modeling. So when we look at the in silico aromatase enzyme inhibition to determine the possible binding modes and interaction underlying their activity, we see that compound 1J is settled properly in to the active side of the enzyme. In this picture, figure A represents pose 1 and 2. Figure B represents pose 3 in the active site of HCYP19A1. Hydrophobic and hydrogen P interactions are indicated with dashed lines. In figure A, docked pose 1 is indicated in turquoise, and dock pose 2 is indicated in light brown color. In figure B, the dock pose 3 is indicated in purple. The hem group is shown in CPK representation. For clarity, only the amino acids that participate in ligand protein interactions are shown. All the dock ligands can adopt at least one of these three poses in the active site of HSIP-13A1. Also, we see from this picture the lowest IC50 for HSIP-13A1. Several similar docked poses have been obtained of compound 1J in the active site of the enzyme. And in poses 1 and 2, the phenyl group with its para-chlorine substituent points towards the entrance of the active site, where the electronegative chlorine atom is close enough to the side chain of arginine 192 for electrostatic interactions. Hydrophobic interactions are formed with the side chain of phenylalanine 221. The indole moiety shows flexibility and forms either hydrophobic interactions with the side chain of leucine 477 or with the hem group. In pose 3, the ligand has moved more towards the entrance of the active site and further away from the hem group. The side chain of arginine 192 and glycine 218 form cation P and hydrogen P interactions with the ligand's phenyl group, respectively. The indole group of the ligand forms hydrophobic with the side chain of phenyl 221. So we can say that 5 out of 19 compounds show rather strong inhibitory activity towards CYP19A, as indicated by IC50 values lower than 20 micromolar concentration. Those 5 compounds are shown to be stronger aromatase inhibitors than melatonin, which is their parent compound. However, they have approximately 10 times less active than a well-known aromatase inhibitor, ketoconazole, in our assay. Compounds, especially meta and para-chlorinated 2-methyl indole hydrogen derivatives, seem to be promising candidates for prevention and treatment of ER-positive breast cancer because of their dual benefits as aromatase inhibitors and oxidative stress modulators. But of course, we need more further research on this. In our previous study, we evaluated oxidative stress modulating effect of 2-methyl indole hydrogen derivatives. And this effect of compounds suggests a protective role in breast carcinogenesis as well as many other oxidative stress-related diseases. The present results might be useful in designing and synthesizing novel indole hydrogen derivatives with either more or less inhibitory activities toward aromatase in the consideration of these compounds from a toxicological and therapeutic point of view. And in here, we see the members of our melatonin research group, which is predominantly female, as you can see. There are many young PhD students and colleagues in this group. I am very pleased that 2 Erasmus program exchange students, Natalia from Italy and Eddie from Germany, have accompanied some of our studies. I would like to thank Professor Gürer Orhan for the toxicological studies and Professor Akdemir for the molecular modeling studies of the synthesized compounds. And the Scientific and Technological Research Council of Turkey, TÜBİTAK, for supporting our studies. Finally, I would like to thank you very much for your attention. And if you have any questions, I will be happy to answer. Thank you.
Thank you. Very nice presentations about melatonin analogs, Sibel Süzen. One of the questions is from Professor Hakan Göker. What kind of modifications should be done on the structure of melatonin for expanding the half-life of it?
Thank you very much. Before I start answering the questions, I would like to congratulate you, Professor Bosker. It was a very difficult job to organize such a big event online. So I'm very proud of my faculty that organizing this huge event, so many participants in this meeting. Thank you again and congratulate again the organizing committee, social scientific committee, and whoever works in this symposium. It is very important for me because I was only a master science student when we had the first ISOPS meeting. So it is very also emotional to have to see how we become so big. Of course, this work is a preliminary work of a research on breast cancer. Aromatase inhibitors is a very important maybe subject that we can inhibit this enzyme and help to ER positive breast cancer type for the therapy. Before we start the work, we actually were searching the antioxidant activity of melatonin. But by the time we realized there are many other effects of melatonin and melatonin analog compounds. Of course, these analogs, why we designed that, the first problem was melatonin is not proved as a drug. The FDA so far didn't approve melatonin as a drug for antioxidant activity. So maybe we can understand that because the half-life is not really high. In 5 or maybe 10 minutes, it goes up in the blood. The concentration goes very high. And so efficacy as a drug is not really maybe accurate for treatments. That's why we started to make modifications according to increase the antioxidant activity. So we have done many research on these activities. So we realized the activity increased addition of different groups. So what we realized, addition of the chlorobenzene type or halogenated phenyl type groups increased the half-life of melatonin. Of course, these are all belongs to in vitro studies. So when we realized we increased with the in vitro studies, then we started to do some anti-cancer research because the dual effect of melatonin also effective on our compounds. So we, as I mentioned, it's quite a preliminary study, but we realized we were right to guess that we have dual effect on these cancerous cells. Of course, we can do many more modifications, but so far the molecular modeling of the enzyme showed us we are going on the right path so far to make these modifications. So thank you very much for the question, and thank you for my invitation, Professor Bosker. Thank you.
Thank you again. The other question is Murat from Murat Kışla. He said, Dear Professor Suzanne, I would like to thank you for giving us the valuable data and much detailed study. My question is about the molecular modeling part and the involvement of the CAP enzyme in the docking study. Can ER-alpha be another docking target simultaneous with the current docking target, since that was mentioned in conclusions? Thanks in advance.
Yes, of course. It's a good question. We have other opportunities, or we have other selections. Why we have chosen these? Actually, we screened the similar studies because it's a very well-known enzyme, and there has been maybe hundreds of studies so far using these docking studies on these molecules. So we have screened, and we decided the most accurate ones to use. Of course, there are other options. So we used the ligands were docked into the HCP19A1 structure. PDP entry is 3S79, and so we're using to P450 enzyme setting and the gold scoring function in the gold suite software pack. The binding pocket was defined as all residues within 12 angstroms of atom C10 of the co-crystallized inhibitor SAD. These are our findings, the best results, but of course there are other options. Thank you. We can't hear you, Professor Bosker.
Thank you very much again, Professor Suzanne. Very nice presentations and explanations. Thank you again.
Thank you.
Now we are transfer the other speaker, second speaker, İlker Ateş. Yes.
I'm here.
I'm go.
Okay. Thank you for giving me the introduction, a chance of introduction. This is our second lecture. Dear participants, now I want to introduce our second lecturer for the opening ceremony, Mr. Ercüment Çiçek from Bilkent University, Ankara. I want to give a short biography of Mr. Çiçek before his speech. So, Ercüment Çiçek earned his BC and MS degrees in computer science and engineering from Sabancı University in 2007 and 2009, respectively. He received his PhD degree in computer science from Case Western Reserve University in 2013. During his PhD, he visited Cold Spring Harbor Laboratory to work on gene discovery algorithms for autism spectrum disorder. After graduation, he worked as a Lane Fellow in computational biology at Carnegie Mellon University till 2015. Since then, he has been an assistant professor in the computer engineering department in Bilkent University and is an adjunct faculty member in the computational biology department of Carnegie Mellon University. His speech is titled as Machine Learning Models for Predicting Drug Synergy and Side Effects. Before his lecture, I want to recognize to you that questions and answers session will be carried out in the chat box. Now I am giving the turn to Mr. Çiçek for his informative lecture.
Hello, this is Ercüment Çiçek. I am a faculty member in Computer Engineering Department of Bilkent University and an adjunct faculty member at Computational Biology Department of Carnegie Mellon University. So today I'm going to talk about our machine learning models to predict drug synergy and side effects, which is a joint work with our PhD student Halil İbrahim Kuru, MS graduate Onurcan Üner, Assistant Professor Gökberk Cimbiş from METÜ, and Assistant Professor Öznur Taştan from Sabancı University. Today I'll talk about two of our works. The first one is about drug synergy, drug side effect prediction. This work is on bioRxiv. You can reach it through the QR code here. The second one will be about the synergy prediction, which is just accepted to IEEE ACM Transactions on Computational Biology and Bioinformatics Journal. So let's focus on drug side effect prediction first. So an estimated R&D cost for a new drug is around $2.6 billion, which is very costly. And the probability of a drug passing the clinical trials and entering into the market is around 10%, which is very low. So the failure rate in the early phase is around 70%. You might expect that in the later stages, this is quite low. It's actually not. So 50% of the phase 3 trials fail. So this creates a lot of problems, obviously. The financial costs. For instance, Vintafolide, which is a platinum-resistant ovarian cancer drug, failed the phase 3 trial. This led to a 62% slump in the share price of the company who produced this drug. The primary reason for drug failures in clinical trials is the safety and unforeseen side effects, which constitute 17 to 30% of phase 3 drug failures. So, for instance, this drug pembrolizumab, targeting multiple myeloma, failed phase 3 trials, and it led to more fatality in treated group compared to the control group. So you might think there are not many participants participate in phase 3 trials, but actually between 2012 and 2015, 150K participants volunteered for phase 3 trials. So this is a really a big issue on patient and volunteer safety. So we propose computational methods which pre-screen drug candidates for possible side effects. And even before going into clinical trials, researchers can have an idea about possible side effects and maybe not pursue that drug at all. So there's a big literature on side effect prediction. Various algorithms proposed using chemical structures of the drugs, drug protein and protein-protein interactions, along with metabolic network and pathway activity levels. So these features are nice for this task, but the problem is you cannot find all such information for every drug, every compound. So this leads to small data set sizes, which is a big problem for machine learning models. And moreover, the works in the literature usually do not focus on the context-specific information, like the cell line gene expression changes with respect to certain dosage or other factors. So they only rely on existing knowledge and try to come up with a global prediction. So there's just one work, which is the one cited below, Wang et al., which used this condition-specific information using the LINX L1000 dataset. So this is their approach. First, they obtain LINX L1000 compounds. So this dataset basically measures the gene expression changes in the landmark 978 genes with respect to perturbation with a compound on a certain cell line. So they say if you know the gene expression levels for these landmark genes, you can extrapolate the rest. So they have around 20,000 compounds. They also obtained the compounds from MLPCN study, which is basically checking or cataloging the morphological features of the cells with respect to perturbations. But then they say it doesn't provide much information about side effects, so then they drop this study. Finally, they obtained the ground truth labels of side effects for drugs from the CIDR dataset, which contains around more than 1,000 drugs. Then they basically generate a feature set per drug. So here you see on the y-axis there we have drugs, and on the x-axis the morphological features of the considered cells, but again they dropped this. They contain 166-bit max fingerprints for each drug, and then they contain the gene expression levels for these landmark genes for every drug. So they generate a data set like this. They use what's called a multi-label classifier, which I will talk about in a minute. And then they learn how to predict the side effects using these features. And then they basically, after you have a drug for which you don't have any information about the side effects, you can predict if it will cause these 153 side effects. So they output per drug, so per drug they output a vector which indicates if that drug may cause that side effect. So the method that they use is called extra trees. If you are familiar with random forest, it's very similar. So they input the full data set instead of generating bootstraps. So on that data set with some extra randomization, they fit decision trees, many of them, and then this basically generates a forest. Every decision tree has a prediction about a drug having a side effect, then the consensus of them becomes their final prediction. It's a simple method, kind of an old method from the literature. And then this figure on the right bottom basically reports their results. They find that the best results obtained with a combination of the chemical features and gene expression levels for the drugs, and then they achieve AUC at about 0.67 level. So this is their final result. This is how the Lynx 1000 dataset looks like. So this is the pipeline of data processing. So they have many levels from going from the raw data up to the signature level. So at the fifth level, for every drug perturbation, you obtain basically a signature gene expression level. So, this data set contains many replicas, around 500,000 experiments for more than 20,000 drugs. But Wang et al. Study gets only a single experiment for each and every one of the 791 drugs that they consider. And they fit their extra trees approach to this data set to predict the side effects for new drugs. So what we said is, since this is a simple model which works on a small data set, can we use more complex deep learning methods to utilize more out of this data set? Because they are discarding so much information. And our goal is to improve the state-of-the-art prediction performance, which also considers this condition-specific information. So the name of our method is called DeepSight. Here I'm listing the features and labels that we are using to train our model. So we use more than 18,000 experiments available for the same set of 791 drugs. Again, we are using the same max drug fingerprints that Wang et al. Uses. In addition, we also try to use SMILE strings, which are obtained from the PubChem database, and we find that they are quite useful. We also add some meta information about the experiments, like the cell line on which the experiment is performed, the timing of the experiment, the dosage information, and so on. Then we try various deep learning neural network architectures to extract more information from this dataset. We again use the same label dataset, the CIDR database, to obtain the ground truth side effects for the drugs. Finally, we also use a side effect ontology database called ADR-ECS to group similar side effects, which is going to be used in one of our deep learning architectures. I will talk about in a couple of minutes. So the first architecture that we consider is a basic multi-layer perceptron. For this, we basically obtain the CS fingerprints, and which is the chemical structures, and then the gene expression changes in the cell line for this perturbation. We concat them and feed through a multi-layer perceptron. So the blue boxes over here are the layers of the neural network. In each layer, we have multiple neurons, and all neurons in level K is connected to all other neurons in level K plus 1. And we have a loss function, which basically indicates how well we are doing in terms of predicting the side effects with respect to these the current set of parameters we have, and guides us to learn better parameters. So by parameters, I mean we are learning the strengths in between these these circuits, which are our neurons. So which connections among these neurons are more important is learned by the model, and after training, we can predict if for given CS fingerprints and gene expression profiles of an experiment, which side effects are going to occur. So the second structure we considered is called a multimodal neural network. So the difference here is that we don't concat the features and then feed it to a network. First, we feed individual features into two feature-specific subnetworks. They learn a transformed representation of these features, and then we concat them. Then that is fed into a multi-layer perceptron, which lets us predict side effects for a drug. The third architecture we consider is a multitask neural network. So this considers the side effect grouping. So everything is same up until the end of the first n layers. So it's just like a multi-layer perceptron, but then the output of this multi-layer perceptron are fed into multiple small multi-layer perceptrons, which only consider side effects that are related. So side effects related to cardiac disorders or eye disorders and so on. So the idea here is that if you learn something about a certain side effect, which is quite similar to others, you can share this information. You should not treat them as independently. So this comes from the machine learning literature, which indicates that you do not have to learn everything from scratch, which requires a lot of data. As humans, we are really good at generalizing. One basic example is that if you know how to drive a car, then maybe driving a truck is different, but you have an idea about the steering wheel and so on, so you can transfer that knowledge with some additional information. You can drive a truck. Similarly, you don't need to learn treat every side effect as independent. If you learned well for one, and if you know the other one is quite related, then let's reuse that information so that you don't need as much training data. So we are doing it for the side effect classification here with the hope that our performance of prediction is going to increase. So the final architecture that we consider is a SMILES convolutional neural network. So here, instead of max fingerprints, we are using the SMILES representation obtained from PubChem. As you see on top, we have the SMILES representation of a drug. The sequence length is the SMILES representation length. Then for each index of our SMILES representation, we have what's called a one-hot encoded vector, meaning so only one of the boxes in each column is going to be one, representing an orthogonal representation of each atom or a group. So in short, we obtain for each drug such a binary image. So white boxes are 0, black boxes are 1. And what we apply what's called the convolution operation on this image. Again, from the machine learning and vision literature, convolution is an operation which applies a small window, a sliding window on this image. So you will have like a vector of 5 indices, which is going through this image, trying to capture information from 5 neighboring pixels or indices in this case. So the idea is neighboring positions in the SMILES string are related. So if you have 2 atoms that are closer on the SMILES string, SMILES representation, it means they are more closely related than 2 atoms that are on the opposite sides of the string. So we basically exploit this locality of the information by moving multiple sliding windows on this image with varying sizes, which are also called kernels. So we have kernels of size 1, 2, up to 200, each of which learn a different representation for this image. And then the outputs of all these convolution operations are concatenated at the very end, which is passed through a classification block, which is a multi-layer perceptron, just like we did in the multimodal representation case. Let me talk about our results a little bit. So the first row over here you see is our baseline, the Wang et al. Paper that we try to improve. First thing that we do is we use our most basic algorithm, multilayer perceptron using the exact same set of training and test examples, but we use only the chemical structure, not gene expression. And we see that we have more than 11% increase in the macro AUC and 1% increase in the micro AUC. So this shows that using a more complex algorithm than the extra trees already helps improving the state-of-the-art performance. Now we set this as our baseline and try to improve our results. Checking only using only gene expression data with the same architecture does not provide us such good results, indicating chemical structure is an important factor in predicting side effects. Then we join them, gene expression and the chemical structure, and we now use extra gene expression values that were discarded by Magneto. We have better results than gene expression alone, but lower results than chemical structure only, indicating that the extra replicates in this data set are actually adding noise while being still informative. Now, when we join gene expression, chemical structure, and metadata about the experiments, we still obtain good results, but not still as well as chemical structure only. Then we go ahead and try more complicated architectures like the multitask network, multimodal network, and find out that the multimodal network that we considered provides the top results with 0.79 macro AUC and 0.87 micro AUC, and provides the state-of-the-art results. So this shows that the using gene expression and chemical structure and extra replicas in a more complicated architecture achieves the state-of-the-art result. Then we try our SMILES representation as SMILES-CoV architecture. So here, this is kind of different than the previous set of experiments because due to varying lengths of the SMILES strings, we had to do some further pre-processing of the data and had to get rid of some of the drugs. So now we have around 400 training samples and 200 test samples. But this was our baseline, the best method, the simplest method, which only uses chemical structure. We showed that we can improve this further using the convolution operation and SMILES strings. And this achieves the state-of-the-art highest results with 0.8 macro AUC and 0.88 micro AUC. So, so this slide basically shows you on the left are the easiest to predict side effects like Cushing syndrome. You can really do well with that. And on the bottom, the hardest side effects to predict with relatively lower positive samples. So the drugs with these side effects are not much. And we had hard time in predicting these side effects. On the right here, you see that our top 10 false positives and top 10 false negatives. So our grantor says this drug does not have this side effect, but we are really confident that it should. So first checking for this compound, if it causes anemia, actually we had found that even though CIDR dataset does not contain this side effect, NIH toxicology dataset contains this information. So this really causes anemia. And we check if this compound causes vomiting. We find a study in the literature which has 152 participants getting this drug. 62 of them had side effects and 19 of the 62 had vomiting, indicating that our prediction is correct. And checking through commercial sites on the web, which are questionable in terms of their reliability, indicate that 9 out of 10 of these predictions are correct. But again, we cannot say for sure since they are not really that reliable. Going through the false negatives, we see that, for instance, these two drugs, in our ground truth, it's said that these two drugs indicate these side effects. But we find evidence in literature that these drugs are actually used to treat these symptoms. They are not really their side effects. So indicating that our predictions are sound. So my conclusions is we couldn't find evidence for gene expression providing the context-specific features, providing a major leap in performance. But still, it is an important aspect to improve on the state-of-the-art results. We had shown that complex models can leverage input features better, and that the small string provides better, using small strings provides better results compared to using max fingerprints. Now, I want to talk about a little bit about our synergy prediction task. So, as you know, in cancer, drug resistance is common, and usually a single drug is not a solution. Combinatorial drug therapy has been a very effective strategy, but you cannot check even every pair of drug combinations exhaustively, even using high throughput screens. So the goal is to use, again, computational methods to prune the huge search space and guide high throughput synergy screens. So similar set of features used in this task as well, just like side effects. And again, the problem persists that the datasets sizes get smaller, prohibiting using more complex models like deep learning if you try to find all these information for all drugs. You cannot, so you have to use a smaller subset of the drugs for your training. There are only two algorithms that uses the chemical structure, which is widely available, and the gene expression information, which we use for side effects as well, in this task now to predict synergy. The first one is deep synergy, and the second one is tree combo. The first one is a deep neural network-based algorithm, and the second one is just an application of a well-known tree-based algorithm called XGBoost for this problem. So we find a very large database called DrugComp, which basically combines all available studies that experiment for drug synergy. This is, as you see, the initial data set that we consider DrugComp contains close to 500,000 combinations of more than 4,000 drugs, and with experiments on more than 112 cell lines, more than 100 cell lines. So in table 2, you see the breakdown of individual studies that DrugComp combines. We had to do some feature filtering, duplicate removal, and we are working with basically close to 300,000 combinations for slightly more than 3,000 drugs on 81 cell lines. So on the left, so the name of our architecture and model is called Matchmaker. And on the left, you see the architecture of Deep Synergy, our competitor. Basically, they combine the chemical structures of the two drugs with the cell line response, I mean the landmark genes, and they pass it through a multi-layer perceptron, which has 2 layers, and predict the synergy score, which is the lowest score. Instead, what we do is, just like we did in the side effect prediction, the best model was, remember, the multimodal model, which basically considers each feature independently first, multiple modes, and then combines the transformed features. We do the same here. So we get the chemical representations of drug A. We match it with the cell line response. We feed it through the first drug-specific network. We do the same for drug B independently. So 2 networks first learn a transformed representation for this drug's effect on the cell line. And then the joint representation is passed through a 3rd network, which is called synergy prediction network, to predict lower synergy score. Here you see our results. So here the task is regression, meaning we are predicting the exact lowest score. On the left, you see the mean squared error, Pearson correlation, and the Spearman correlation of our predictions. So Matchmaker provides the lowest error and the highest correlation in all metrics when we compare with the methods from the literature and some other baseline methods. So this was regression. On the right, you see our results for classification this time. Usually people do not the researchers do not focus on small lowest scores like +1, +2, or -1, -2. So they usually care about large magnitude results like more than +10, so high synergy, less than -10, high antagonism in this case. So we are showing the ROC curves when we discretize our predictions. If they are larger than 10, less than then we predict synergy or antagonism. Otherwise, we say there is no interaction. The blue curve over here, as you see, dominates all others, which indicates the highest AUC and the best classification result. We also applied the algorithm on individual dataset to see if our results generalize. Here again, we see that on the ONAIL dataset and the Almanac dataset, still Matchmaker provides the best results compared to our competitors. Here I'm showing you our top predictive drug pairs, indicating we are doing a really good job to predict the synergy of these drug pairs, just for your reference. And here I'm showing you our top most confident 25 wrong predictions. So here you see the actual lowest score here in the middle. So for instance, for this one is highly negative, whereas we are predicting quite positive level value. And then we are checking 5 other scores of synergy. If they are all indicating what we predicted, meaning a positive score, we say this is high support. And we check the literature, we find that these two really interact, and the first one affects the concentration of the second in the blood serum. And for instance, for these two drugs, we find that they really interact, they are synergistic, and once administered together, they result in prolonged survival. And in this cell line, actually, once they are administered together, they decrease the expression of a DNA repair enzyme called MGMT, which again results in prolonged survival. And here we see that most of our false predictions, most confident false predictions are on T98G cell line. This is actually the cell line on which we have had the hardest time, which might indicate there might be a systematic error on the experiments performed on this cell line. So to conclude, combination therapy is important for cancer, and we had shown that Matchmaker outperforms all the state-of-the-art approaches in this field, which can be used for combination therapy prioritization. So currently our model is trained for cancer synergy, since that's the data available, but it's possible to fine-tune it for other cell lines and other diseases if researchers have data. So thank you for listening to my talk. I would like to first thank to my collaborators and all the organizations below who support our research. You can get more information about our research in this URL. And if you have any, I would like to take questions. Thank you once again.
Thank you for your awareness-raising lecture, Mr. Çiçek. It seems that new algorithms or models will help us to predict the synergies or side effects of the chemicals or xanobiotics now or in the future. So let's go on with the questions. I want to look at the chat box. Are there any questions? I don't see any question in the chat box. Okay, one question came from Murat Kışla. I'm reading, Professor Çiçek, thanks for the highly technical presentation. Besides the methodical part for deep learning, my question is about the chemical part. What can be other inputs for the molecular properties, in situ results or QSR parameters, etc.?
First, thank you for inviting me to this nice symposium and allowing me to share my research. To answer this question, basically anything that you might think that might help in predicting side effect or synergy might go into our predictions. We try to keep it as simple as possible. So the chemical fingerprints and the SMILE strings are available for almost all compounds out there. So in order to be able to come up with such a model, a computational model, you need large amounts of training data. And if you do not have that information for many of your examples, many of your drugs, it means it's not possible to come up with such an algorithm. So for that reason, we try to keep it as small as possible, just drug fingerprints plus cell line gene expression to include context-specific information. But if you have a property which you think that affects the side effect of a drug, for instance, you can easily add that into our model. Usually people focus on the interactions between drugs, for instance, on protein interaction and interactions between drugs and proteins, the interactions among the proteins, and include that into the model. But then it means you need to know those interactions for many of the drugs, which is usually the problem. Then you need to go for simpler models. Or people add other omics data, like it could be protein expression, for instance. I wish we had more data. But again, the problem is scarcity of the data and not having a complete data set. If you have any information about a drug, and for all drugs, then you can use them all.
Okay. Are there any questions? Murat, thank you for the answer. I see no one is asking question. Okay, then I want to thank you again, Mr. Çiçek, for your participation in our Congress. So I want to give the turn to other lecturer or other lecture to Burcu Devrim Gökberk. Thank you again for your participation.
Good morning, dear participants. Last speaker of this session is Dr. Mustafa Diken. Dr. Mustafa Diken received his PhD in tumor immunology from Johannes Gutenberg University, Mainz, and is currently serving as Deputy Director Immunotherapy Development Center at Translational Oncology Institute, and as Vice President Vaccines and Immunology at BioNTech. His research focused on the development of novel cancer and infectious disease vaccines based on antigen encoding messenger RNA and the elucidation of immunomodulatory mechanism for cancer immunotherapy. His other scientific interests include assay development for preclinical evaluation of cancer vaccines. His research led to novel mRNA vaccines, which are currently being tested in several clinical trials, and the development of an mRNA vaccine against SARS-CoV-2. Dr. Diken is also the scientific secretary of the Association for Cancer Immunotherapy, a non-profit organization aimed at advancing cancer immunotherapy. Now, I give the microphone to Dr. Diken to make his speech.
Hi everyone, this is Dr. Mustafa Diken. Today I would like to give an introduction to mRNA vaccines and explain a little bit what we achieved in the last 2 decades with mRNA. Before I start, I would like to thank the organizers for inviting me to this nice meeting. So let's get started. So first I would like to give some information on the city of Johannes Gutenberg, Mainz, which is located in the middle of Germany, quite close to Frankfurt. I had to make this explanation before, but I think many people know where Mainz is, thanks to the success of the SARS-CoV-2 vaccine. So we have a big university medical center in Mainz, and then a university named after Johannes Gutenberg, and we have an association for cancer immunotherapy, for fostering research in cancer immunotherapy, and we have 2 important institutions, one being TRON, Translational Oncology Institute, and the other one is named BioNTech, which does not need any more introduction, I guess, after last year. Both founded by Professor Uğur Şahin and Özlem Türeci. So I'm employed in both of them. So mRNA is a very versatile format. So there are different uses of mRNA, ranging from cancer immunotherapies to genome engineering, or as we all know, infectious disease vaccines, but RNA can also be used for genetic reprogramming, either directly or via ex vivo transfer of the cells modified with RNA for better therapeutical success. So what we did from the beginning is to shortcut these long preparation steps and directly administer the mRNA either intranodal or intravenous or lately intramuscularly. So how do we call the RNA vaccine? So we generate our RNA vaccine by the so-called in vitro transcription, which can be used or started with a linearized plasmid template encoding your antigen of interest and under the T7 polymerase promoter. RNA vaccines are easy to produce and purify, and we can easily introduce and modify sequences that we want, and there's no risk of genome integration, unlike DNA vaccines or viral vaccines, and it's independent of HLA restriction, unlike peptide vaccines, because here you can use the encode for the whole protein antigen. So we made some structural optimizations in the RNA in the last 2 decades. I'm not going into details, but what I can tell you is we optimized every little sequence partner or domain of the RNA to get much better RNA with increased intracellular half-life, translation, and MHC presentation. And with this modified RNAs, we are 1,000-fold higher expression and other properties of RNA compared to what we did in the beginning of 2000. So what is happening with the RNA when it is internalized by the cell? Actually, before internalization, most of it is degraded by RNAs when it is not protected, and then it is then internalized by endocytosis, mainly macropinocytosis, then it escapes the endosomes, gets translated by the ribosome, just like another RNA produced by the cell, and then the protein is then processed into class 1 and class 2 processing pathways to present the antigens to the T cells. So we started with a systemic RNA vaccines with a big team from Tron and BioNTech, and the idea was to give the RNA intravenously for systemic DC targeting, and we wanted to ensure that we keep the RNA integral. So as I said, RNA is very fragile molecule, so it can be degraded very easily. So you need to protect RNA, then you need to ensure that an dendritic cell or antigen presenting cell mediated uptake. And then, of course, as vaccine developers, we would like to get, in this case, an anti-tumoral T cell response as a cancer vaccine. So what we did is we mixed RNA with the certain lipids or liposomes at different ratios, and then look by in vivo imaging where the RNA goes. Here, when I do not complex RNA with any liposome and inject intravenously, all of the RNA is degraded, and you do not see any luciferase signal in the bioluminescence imaging because the RNA is not there. But when I complex it, I see an interesting pattern of biodistribution that when it is a positive charge, RNA mainly goes to lungs, but when I have a negative net charge, then it goes more to the spleen, and also shown here in the lymph nodes and bone marrows, which are all lymphoid organs. So we looked whether the RNA is really internalized by dendritic cells. For this, we depleted the dendritic cells in a mouse model, and then we can see that the signal is very much decreasing. And when we use an EGFP encoding RNA to look in flow cytometry which cells are expressing the EGFP, we can see that the dendritic cells are mainly taking it up, followed by macrophages, but the other cells, in this case the spleen, hardly internalize and express the RNA. So interestingly, RNA also activates the immune system intrinsically, and we can see the activation of the dendritic cells, but also other cells, although they do not internalize it. And this can be explained by the detection of systemic interferon alpha, and each cell of our body has an interferon alpha receptor, and this can activate those other immune cells, creating an inflammatory environment in the lymphoid organs. So as vaccine developers, we looked at whether we can induce T cell responses using some model antigens with repetitive immunizations of RNA. We used around weekly immunizations of RNA, and then we can really induce high frequencies of antigen-specific CD8 and CD4 T cells, and these cells really kill targets in an in vivo cytotoxic assays. And to our surprise, when we block this interferon alpha secretion that I mentioned to you, we still get T cells, but these T cells become non-functional, so they really hardly express these effector molecules like interferon gamma and coenzyme B to kill the tumor cells. And very important feature for a vaccine, we can generate T-cell memory and reboost these responses, for example, coming 60 days after the last immunization and then re-injecting the RNA vaccine, and then we can really lead to proliferation of T-cells. So we can really bring them the RNA to the dendritic cells without degrading it, and we can induce T-cell response, which is really good. But we get also anti-tumoral responses. For this purpose, we use different tumor models. Here's an example of head and neck cancer in mouse. When here each line represents represents a tumor of a mouse, and when I do not treat the mice, the tumors grow. When I treat the mice with an irrelevant RNA not expressed by the tumor, so not a tumor antigen, that they still grow. But when I use E6 and E7 encoding RNAs, which are two HPV-derived genes expressed by this tumor model, the tumor shrinks and disappears when I start on day 7 or day 10. Here's another model with melanoma with a TRP-1 vaccination expressed by the tumor. The same picture when I immunize, the tumors are shrinking. And this is a lung model that the tumors are in the lung, so they express melatonin, therefore you see black. And they are also gone when I immunize it with our RNA vaccine. This is another colon carcinoma metastasis model that they go to the lungs, and this time we are not seeing the RNA in colorful BLI imaging. It's now the tumor cells expressing luciferase and growing happily in the lungs of the mice, and when I inject my RNA vaccine, then they are lost because the tumor cells are killed by the T cells that I induced with the vaccine. And last but not least, here again, when I block the interferon alpha signaling, then the T cells I induce are not 100% successful to control the tumor, and we get some tumor cells as well here. We can combine these RNA vaccinations with other standard of care. Here, for example, we combine RNA vaccination with irradiation. Neither RNA vaccine alone or the irradiation is effective to fully eradicate the tumor, but when I combine them here in dark green, they can really eradicate the tumor. Just of note, I'm using here a single RNA vaccination because when I immunize 3 times, the picture will look like this, and just to show you the combination effect, we are just immunizing once. This is another example with chemotherapeutic agent, same picture. To each alone cannot prevent the tumor growth, but with combined together, this is really effective strategy. So the way that the RNA vaccine, the systemic RNA vaccine against cancer works is that we bring our RNA lipoplexes to the lymphoid organs like spleen and lymph nodes and bone marrow, and there they are taken up by antigen-presenting cells, and they present the antigen to the T cells in an activating environment, and these T cells primed and then go back to the tumor and kill the tumor cells. So we translated this into the clinic, the phase 1 clinical trial in melanoma patients with 4 different antigens. And here, just to recapitulate, so you see the spleen picture in the mice, and we had a similar spleen targeting in patients because we can see activity in the spleen. And just some clinical activity to show you, we can see eradication of the metastasis in these patients, the lung metastasis. Here, another one that the patient did not respond to checkpoint inhibitors before, but when we combine later on with the vaccination, then the metastasis disappear. This is the overall picture of either monotherapy or anti-PD-1 therapy showing the efficacy of the vaccine with shrinking tumors in also patients. So, of course, personalized immunotherapies also emerge and diverge in a way that instead of this stratified targeted medicine that we, for example, have 3 patients, we make in vitro diagnostics, and one of them is positive for the target, for example, HER2-NOI, a known target in breast cancer, then only this patient gets the Herceptin, but the others do not get it. Instead of this type of strategy, we would like to have a personalized monoclonal vaccine in which we design tailored vaccines against the mutations of each and every patient, specific for each of them, so that everyone can have access to the therapy. So for this, we also make use of RNA. We identify the mutations of the patient, prioritize them for their immunogenicity, and then make an RNA vaccine encoding for more than 1 mutation, and then inject it. And this is how the process looks like. I'm not going into details, but I just want to say that it's a complex but coordinated process. Here is the tumor sample of the patient coming. Here is the blood sample of the patient coming serving as a normal tissue. And then we have all these steps to have our drug product, the RNA vaccine, to be injected to the patient. This was also tried in a clinical trial and was very successful, showing both de novo, that means these responses to these mutations were not evident there, but after vaccination we have them, or in dark green, the patient had already pre-existing immune responses against these mutations, and we augmented these responses with our RNA vaccine. So of note, these patients have had an excellent safety profiles with our vaccine, so no adverse side effects. And then, of course, nicely, the patients did not have significant amount of metastasis after the RNA vaccination, and this is right now even more for 5 years follow-up, while they had a lot of different metastases before the vaccination, showing that the efficacy of the vaccine and reduced metastatic recurrence rate after our vaccine. Now I'd like to switch gears a little bit. So what I showed you was how we use the RNA vaccines for cancer, but now I'm just do the opposite thing. I would like to use it against autoimmune diseases, which we recently published. So in the autoimmune diseases, the balance between the regulatory T cells and effector T cells are demolished, that the effector cells then harm healthy tissue, and then we would like to bring it back to a tolerance-promoting medium, because we don't want that our immune system attacks our own cells. And usually this is done by a couple of different drugs existing, but they are not so specific. So we would like to have a targeted treatment. So what we did is that we target again the dendritic cells. So they're key players. They can do different, can play different roles, like depletion of effector T cells, induction of tolerized T cells. Also, they can help development of Treg cells, and these Tregs can then mediate the tolerance. So what we did is just modified the RNA in a way that it becomes non-immunogenic, so it's not activating the immune system anymore. Thereby, without this activation, instead of the DC activating the T cell that I showed you before for the cancer vaccine, that it's just bringing it to either an anergic state, or it turns into a Treg cell, and blocking the effector T cells, and ultimately the DC lost the ability to induce the effector cells. So let's see how we did it. We modified the RNA with M1 pseudouridine and did again similar experiments for activation, and you can see that this activation that I see with the standard RNA in red is then lost with the non-immunogenic RNA in blue and all cells. And also I don't see any more interferon alpha, which I showed you in the previous section. And then I see also a higher and longer expression of the RNA. Then we look whether I can induce really antigen-specific CD4 T cells that are there, that I can see them with tetramer in this case. But compared to the immunogenic RNA, these T cells do not anymore secrete interferon gamma, so they are not secreting interferon gamma. Instead, they just secrete more, or let's say less inflammatory cytokines in blue compared to the red one with the standard RNA. And these CD4 T cells specific for MOG that I induced with my RNA have more like a Treg phenotype, and then they just suppress the proliferating T cells, and they have also molecules like TIGIT, TIM3, PD1, CTLA4, LAG3. They're all involved in immune suppression. So I can induce with my RNA this time T cells of suppressive phenotype. And I tested them also together with the team in an EAE model, so experimental autoimmune encephalitis. That's a mouse model of MS, in which that we induce the disease with the MOG peptide, and then the T cells that are specific go to the central nervous system and damage the myelin sheath, and therefore we see so-called EAE scores that paralyze the mice in different extremities. So what we did is here you can see when I vaccinate now the irrelevant RNA, it's not helping the disease recovery. But when I immunize with non-immunogenic RNA, then this is really nicely preventing the disease. And you can see that we don't have any more of these effector cells in the brain or spinal cord. And also you can nicely see that in the control and irrelevant RNA immunized mice, the myelin sheath is gone, so very much damaged, but the ones that are immunized with the non-immunogenic RNA, they are really intact. So we can also use a more complex system where we can induce the EAU with the PLP peptide, but can still use mock peptide or PLP peptide to prevent the disease, which most of them are working, and then we can induce both mock and PLP specific T cells that are of suppressive phenotypes, so they express FOXP3, so they turn into also Tregs. So here, mode of action for this autoimmunity setting is actually the same thing is happening, but this time we are giving the RNA in a non-immunogenic fashion. And instead of activating the T cells this time, it just suppresses the autoreactive CD4 T cells, either killing them or giving them a tolerized phenotype, or inducing or converting them to effector Treg cells, which can further suppress these effectors, preventing this effector T cells that damage the tissue to stop to work. So last but not least, I shortly talk about the mRNA vaccines as a pandemic vaccines that we've seen in the SARS-CoV-2 setting. So we could really get the genetic information and then design RNA very fast, encapsulate into so-called lipid nanoparticles, and then started clinical testing last year. This was the time that the SARS-CoV-2 genetic sequence was made public in January 12, 2020, and then we really finished in less than 1 year phase 3 trial with an efficiency of 95%, and the global rollout has begun after that in many countries after that, and this was a really fast but also effective system to test and show the premise of the RNA vaccines. And just I'm not going into details, but here it's very simply the RNA is encoding for the S protein of the SARS-CoV-2. Then we can induce S1 specific IgG in mice and also in man, and also these antibodies can neutralize the SARS-CoV-2 in vitro, and we can also induce both CD4 and CD8 T cells, both in mice and also in human, just to show that we have the full arms of the adaptive immune system to really fight against the virus. It's a prophylactic vaccine, of course. And here's the data for the human from the phase 3 study that right just after, as early as 12 days after the first dose, the protection begins, and then it reaches 95% efficacy. And I'm sure you've seen other reports on this. With this said, I would like to end and thank, of course, Professor Schrein and Sam Trigi and Christopher Huber, founders of Tron and BioNTech, and Krista Krinkel for the autoimmune work, Lena Kranz for the cancer vaccines work, and all the other team members from BioNTech and Tron, and of course on the University Medical Center, who also helped us with the clinical trials. So with that said, I would like to end and would love to get your questions. Thank you very much.
Thank you very much, Dr. Diken, for your very informative speech. There are any questions? Yes, there is a question from Dr. Ongun Mehmet Saka. Because of easy fragility of mRNA, cold freeze is enough for stability, or do you prefer other combined strategies?
Hi, sorry. I just had the chance now to unmute. I think when RNA is complex, it's not so fragile anymore, and we now have convincing data that it can be stored also at 4 degrees for quite some time. Of course, in the long run, techniques like lyophilization can come to question, but right now, especially for the SARS-CoV-2 vaccines, I think we have very good stability for the worldwide distribution.
Thank you, Dr. Diken. Are there any questions? There is another question from Nurten Altandar. My question is about autoimmune antibodies. Does it trigger autoimmune antibodies?
We have not observed any autoantibodies or anti-drug antibodies against RNA so far. In any of the studies we had, we also had previously cancer studies, and also other academic researchers or companies worked in mice and in human have not observed any antibodies against RNA.
Thank you for your answer, Dr. Diken. Are there any questions? Yes, there's another question from Kıvılcım Öztürk Atar. It's really exciting to see this promising result in the treatment of cancer and autoimmune disease. Should it be a personalized medicine for autoimmune disease patients? And do they have to take the medicine constantly?
Yeah, indeed, that's a very good question. It depends on the nature of the autoimmune disease. For certain autoimmune diseases, the target antigens are well known and characterized. For those patients or for those diseases, of course, we can simply let me share also my video. Okay, perfect. So we can simply use the antigen for the whole population, so it will be effective. But for certain other autoimmune diseases, the antigens causing the disease are not known or can be really specific for a given patient or patient groups. For those, we can first screen maybe for those antigens and then develop a personalized RNA vaccine for those patient or this for the specific patient or for those patient groups, which might be then really tailored for their needs. Exactly, and whether they have to take the medicine constantly. I think with the RNA vaccine, our idea is to really train the immune system in a way that we form memory Tregs and memory T cells. With that, hopefully, it will not be a constant medication, but maybe we can come up with some boost vaccinations in certain time points, but definitely not something that you take or you get vaccinated every day or week. So it's much broader intervals.
Another question from Luca Sansineto. Thank you very much for this really interesting presentation. This is a really prevalent topic. What do you think about the vaccination with the two different vaccines?
I think it's hard for me to comment on this. I can only comment on our own vaccine, but I think there are more studies coming up for these heterologous vaccinations, either first ours and then others or the other way around. So we need to look at more data for this.
Okay, thank you. Are there any questions or any discuss? Okay, I guess we have finished with the question. I would like to thank all session speakers for their contribution. This section is over. Enjoy the rest of the symposium.
Thank you.
Thank you again.